Hi everybody, this is a second video for lesson 1.1 in the Intro Calc course. And for this video I'm going to just go through one example and again use technology to help me figure it out. Once again I'm kind of sticking to a physics example. It's not that this kind of math isn't something you can apply to the other sciences as well, but this fits in pretty closely with what you learned in grade 11 pre-calculus and in the physics that you learned in grade 10 science. This kind of math wouldn't actually hit chemistry until you've done some advanced reaction rate and concentration rate gradients. Those are going to give you graphs that have curves that you'd use calculus on. In biology, I guess it'd be things like population statistics. I can't think of anywhere else off the top of my head that I've ever noticed the need to analyze curves that deeply in biology, but I'm sure there are people out there who could tell you much better than me. Calculus is kind of the language of how we study the sciences, because so often in the sciences we need to know how things are changing, and specifically we need to know how things are changing right now. So we'll start with this problem. Feel free to pause the video if I'm going too fast and you want to copy it down. Example 2. A ball is thrown upwards from the top of a building on the moon. I don't know why I don't think we have any buildings on the moon, but well, we'll just pretend. Its height is a function of time, and there's the equation that describes the height as a function of time, where h is height in meters, t is time in, I believe it's seconds. Yep. And okay, I'll give you a sec to catch up to that. If you need to pause the video to do it, please do. So there's the equation. I'll just move this so that we can see the equation, but we can also see the actual questions that are being asked here. So that's the equation, and from that equation we would like to know the following. A, what is the maximum height the ball will reach? B, how far from its launch point will it be when it hits the ground? And C, how fast is the ball traveling at the 6-second mark of its journey? So at time equals 6 seconds, exactly how fast is it traveling? So A and B you could have answered using just plain old grade 11 mathematics, but it wouldn't have been easy grade 11 mathematics, because let's sketch the situation. Oh, and I just put a little note at the bottom. You don't have to write this down if you don't want to. We're going to use technology to help us on this one, and let me show you why we're going to use technology. This is kind of an ugly equation to work with. Let's think about what we know. Oops, sorry. Let's think about what we know about this equation. We know that it is a parabola. We know that if we set t to 0, this will be the t-axis, this will be the h, height as a, maybe I should just zoom out a bit. There we go. Height as a function of time. We know that because t is 0 would give us 15, that's kind of the launching point. So 15 meters is how tall the building is. Once again, I don't think there are any 15-meter tall buildings on the moon, but let's assume we've built some sort of moon base, and it's pretty boring there, so people throw tennis balls or baseballs off the roof just to occupy their time. And then it's going to, like everything under gravity, make a parabolic curve. And I know it's parabolic not just from my knowledge of science, but from my knowledge of the fact that that's what t squared or x squared graphs do. That is a quadratic equation. It's going to make a parabola. And the A question, remember, was what is the maximum height it will reach? So I'm actually looking for that y coordinate, right? That's what I'm looking for. There's the first thing I'm looking for. Then for the B question, it asks how far from its launch point will it be when it hits the ground? So then I'm looking for this x coordinate. And you might remember from grade 11 quadratics that this, of course, would be the vertex of the parabola. This would be its maximum y value. And this would be the 0, or the x-intercept. Remember, you called them x-intercepts, you called them zeros, you called them solutions of the quadratic equation. And again, let's write the equation down again. It's h of t is equal to negative 1 point, I gotta remember, 162,519, 162,519, t squared plus 10t plus 15. That is not going to be a fun equation to do this the way that we did it in grade 11. Because remember, there's two strategies for finding the vertex. I could complete the square with this and put it into, y equals a times x minus h squared plus k form, and then hk would be the vertex. But think about what it would take to do that to this equation to turn it into this. Step 1 is factoring this 5-digit decimal out of the number 10, which is going to make for a very ugly number to work with, even with a scientific calculator. It'll be a lot of button punching. The other method is that if you're in the form y equals ax squared plus bx plus c, which we are, a, b, c, then x equals negative b over 2 times a is the vertex's x coordinate. So that could give me that could give me this. So let's do that. Let's try that. So this is, of course, x equals minus b over 2a, and let's actually figure out what that is. So that would be minus 10 over 2 times negative 1.62519, and that would be, so let's see, I'll punch buttons on my calculator, and let's see, that'll be negative 10 divided by, open a bracket, 2 times negative 1.62519, close brackets, equals, and okay, so I'm going to get 3.07, I'll just round it to, well, I guess my original function had, what, 5 decimal places, so I'll round it to 5 decimal places. This will be really accurate. So 1, 2, 3, 4, 5, the thing after the 6 is a 3, so I leave that as a 6. So 307656. That's the x coordinate, which is, of course, the time in seconds. So it takes 3.07656 seconds to make it to the peak. And then to figure out what this is in terms of its y coordinate, I'm going to have to find h of 3.0656, which means I have to plug that into the formula. So it's going to be negative 1.62519 times t, which we just found out is this rather ugly decimal, squared, plus 10 times t plus 15. So luckily I have an answer button. That makes the button punching a little more palpable here. So let's see, that's negative 1.62519 times the answer I just had, squared, plus 10 times that answer, plus 15. And that gives me a 30.3828, 30.3828, and then I guess it'd be a 2 meters. And so that's how high this thing goes. So there, all that kind of ugly calculation with decimals just gets me the answer for A. The answer for B is, of course, I have to find the X-intercept. There'll be 2 of them. Remember, there'll be an X-intercept over here as well. But that one doesn't really matter, right? That's not part of the actual physical reality of the problem. This is the one I'm looking for. So I'm going to have to put this to 0, set y to 0, and then use the quadratic equation on this. And this is rather an ugly number to run through the quadratic equation. So I think instead, let's use technology. So I'm going to open Desmos, and let's see, Desmos. I have it kind of something I go to a lot, so it's right there for me on Google. And okay, here's what we're going to do in Desmos. First of all, we're going to enter h of t equals negative 1.62519. I said 9. T squared plus 10t plus 15. So there's the original. Now, as you can see, this is not the most great way to look at this. There's a couple ways you can change the screen. You can just drag things around, scroll in and out with your mouse to do that, but that tends to move both directions at once. If you want to kind of keep this height but stretch your X around so you can see better, what you can do is you can go to the settings for the graph and then just adjust your x-axis manually. So it gives you kind of a domain for the x-axis. So obviously there's no point in going to negative 20 whatever. To be honest, there's no point in going to negative anything. But I kind of want to see the x or the x-axis in my graph. So I'll just go to, say, negative 1. Maybe how about negative 5? There we go. And then for the positive side, we don't need to go nearly as big as 48. So we can go to, I don't know, does 15 work? Actually, even that's a bit big. How about 12? Plenty of size. There we go. We've got a nice looking graph now. Okay, so we used arithmetic and algebra to figure out this vertex very nicely. The program, all you have to do is click in the vicinity of the vertex, and it knows that you want the vertex, and that was the point we found. Now, we actually could get more decimal places than Desmos. Desmos' default is 3 decimal places on most decimals, unless you zoom in. I think if I zoomed in on this point, it would give me more decimals. Oh, no, maybe not. Okay, I'm lying. So anyway, there is a little bit of a decimal loss, but you know what? That's still, when you're talking about seconds and meters, that's pretty accurate, right? If I'm in meters, that 30, that would be, of course, centimeters would be here. So this is to the nearest millimeter. And if you need to know how high a baseball is to the nearest millimeter, that's pretty good. I think we're happy with that. And like I said, it would have taken the quadratic formula with a big ugly decimal to find this, but they find it for us rather quickly. It's 7.4. So I'm going to go back to my page now, and I'm going to start answering some questions. So my A answer, which I did find kind of the traditional way with arithmetic up above, but just reading it from the graph, because again, this is the way I would have done it if I wasn't explaining it. I'd have just gone to here and gone, okay, good. So at t equals 3.077 seconds, my height that the ball reaches, my maximum height, is 30.383 meters. So I'll go height is equal to 30.383 meters. Good enough. So there's the A question answered. The B question, how long does it take before it hits the ground? How far, or how many seconds is it in the air? What's its hang time, I guess is what you'd call that. And again, that would be 7.4 seconds, the x value here. And then remember, that's a height of 0 because you're on the x-axis. So the B answer is time is 7.4 seconds. Now, the next part is going to take a little more work. What I want to do for the next part is, of course, I would like to know exactly how fast it's going at t equals 6 seconds. Now, you're probably looking at going, oh, well, I'll just read the point. There we go, 6 seconds. Now, remember, that's not how fast it's going. That 16.493 is how high it is. How do you find how fast it's going? Well, how fast it's going is the slope of this line, right? Change in distance over change in time. Speed is delta d over delta h, or delta d over delta t. In this case, delta h over delta t. So I am going to make myself a point, and the first point I'm going to put in is going to be the point a, comma h of a. And when I bring up a new variable, I mean, I already have 2 up here. It's going to ask, do I want this variable to be something I can control with a slider? So I'm going to say, yes, please give me a slider. And yes, label that point. And I'm going to move that point to where we want, which is a time of 6. And it can be really picky to try to do this with, oh, there we go. So there we go. There it is at 6. Okay. Now, I am going to now give a point B on this graph. And I'm going to define it the same way. Point B with an x coordinate of B is going to have a y coordinate of h of B. And again, I want a slider. And now I'm going to put that point, say I'll put that point here. So if I can imagine drawing a secant line through those 2 things, that secant line is going to give me an approximate velocity, or sorry, I said that wrong. A secant line from here to here is going to give me an average velocity from, looks like 4.5 seconds all the way to, or is that 5 seconds? Sorry, that's 5 seconds. So from 5 seconds to 6 seconds, it's going to give me an average velocity. I can find that by making an equation. I'll make a slope. But first, I think the first thing I'm going to do is make a line. I'm talking about imagining a secant line. It'd be nice if I could actually see it. So in order to make a line, I actually do have to do the slope first. So I'm going to do the slope. The slope formula, the slope between 2 points, remember, let me just go back to the paper. Remember that the slope between 2 points is y2 minus y1 over x2 minus x1. So now, oops, sorry, I'm not on the screen. There we go. So now look at Desmos. This would be y2. This would be y1. I guess I didn't tell it to label it. Let's see, go back. Label. There we go. So this would be y2, this would be y1. I could run that through my calculator if I wanted to. 6 minus 5 is 1. The denominator is nice and easy at least. But I can get Desmos to do that for me. I can just enter that I would like, and I don't have to type in these decimals. I can just type in what they are. That way if I want to change them, I can just slide the points around and change them. So it's going to be h of b, right? That's my y2. Oh, actually, it's h of a. I should do a first. H of a minus h of b, right? y2 minus y1, all over. To make something all over, just highlight it, and then you can either go down here and find your divide function, or you can use the slash on your keyboard. Same thing. And then over there, of course, I want this x2 minus x1, which is just, in this case, a minus b. If I'd have done this as h of b and that's h of a, as long as I went b minus a, I'd have had the same thing. And there we go. The slope of the imaginary line between here and here is -7. Like I said a minute ago, it'd be nice if I actually could see a line. So I'm going to build a line, and let me go back to my paper. Remember that a line is y equals mx plus b. But what okay, I have an m defined, but for x, I have to put that x in terms of the point A, so that it kind of anchors it to one of the points. So it's actually going to, what I'm going to actually do is y equals x minus a, and then for point B, the intercept, I'm going to just go h of a. So that little formula there will give me a line that for sure goes through a and h of a. So that's what I'm going to actually put in here. I'm going to put in y equals m x minus a, and then plus h of a. And there we go. We've got ourselves, if you zoom in on that, you can see that it's close to the slope that this line is, but of course it's not exact, because it is an approximation. It's the average speed between these 2 points. I guess if I wanted to, I could even put 6 in the middle and say that, well, the point, I want to know how fast this thing's going at 6 seconds. I could go between 5 seconds and 7 seconds. And okay, well, together that means there. Oh, I had it. There we go. That would be a slope of -9.50228, and that's actually, I actually happen to know that that's really close to the actual number. I figured out the actual number. In fact, oh my, scarily, it is exactly the number when you round it to 5 decimal places. That's very cool. But what we can do to kind of make this even more accurate is we can just shrink how close these points are to each other. So we want to know at the point, here I'll even put the point on there. I'll put the point 6 comma h of 6. And there we go. There's that green dot represents the point I want to know the slope at. And I will, watch what happens to the slope. I will just get closer and closer. Now I can't get both of these points or even one of these points right on there and expect to get the slope, because obviously if A and B are the same distance from the origin, if A and B are the same number, I end up dividing by 0, and you can't divide by 0 in math. But notice, the closer I get, the more I get back to that number, that -9.5, and I think it was 0.228. So I can, of course, actually even do this. Watch this. I can change this by sort of manually, just typing in 9, and then here for the A number, 6 point, I could even just call this one 6.0. And there's that number again, -9.500, and that's very close. The exact answer was, in fact, -9.0228. I'm not going to tell you how I found that exact number. I think I will hit it if I keep going here. There it is. It's getting pretty close to that. This digit's an 8 if you do this exactly. There we go. That would round to an 8, so it gets there. Now, eventually the Desmos does start getting stupid. It will not round appropriately. It will eventually run out of its ability to calculate to such small decimal places. Imagine doing this on paper, right? If I was doing this on paper right now, this would be, y2 would be, do I have h of b? I don't know. y2 would be whatever this is when I run it through the formula for the parabola, minus, I forget what the number for 6 was. I can't remember. But anyway, it would also be the number you get when you run 6 through the formula. And the denominator would be hilarious. It would be 6 minus 5.99999. So it would be decimal 0.00001. And by that time, you're getting kind of a ridiculous degree of accuracy. So if I kept adding 9s on here, eventually I guess I've gained a little more accuracy, a little more. There's the 8. Now I think I'm going to overshoot it. Yeah, now it's going to get crazy. And eventually, it'll just say, doesn't exist, right? Eventually, it assumed this number was 6, and then the slope formula went 6 minus 6, which, of course, is undefined. Look, it even rounded it for the two things here. So, again, the real number was somewhere around here. If you're doing your homework, obviously, if you'd have rounded this, I think a textbook would probably have rounded it here. So negative 9.50 probably would have been fine for a slope. So what is that as an answer? Let's go back to the paper. So for the paper, for my C answer, my A is this, my B is that. My C answer is that at t equals 6 seconds, delta y over delta x, or sorry, let's use the variables they have. Delta h over delta t, which would be the actual slope of the line, h of t, which also is change in position over change in time, which is speed or velocity, at t equals 6 seconds equals, what did we say? Oh, my hand just froze. Oh, there we go. Negative 9.50 meters per second. So there we go. So that's a good example of the type of question that you can do using the Desmos technology to help you. There's a bunch of questions in your homework. Here, let me go back to the blog for a second. Do I have the blog open? I think I do. There we go. When I go to your actual textbook assignment, okay, there's a couple of pages here. There we go. You'll see some questions like, here we go. Here's one, like number 7, which I asked you to do, and now it's decided to move on me. There we go. Question 7, like I asked you to do, where it's doing basically the same thing. You're running the number 2 through this formula, and then 1.5, and then 1.1, and then 1.01. Feel free to just make a graph out of this on Desmos. Okay? Enter, this is your f of x. So here, let's start a new graph. New blank graph. So f of x would equal, and okay, so let's see, what was our actual, oh, where did my, there we go. 2x plus x squared. Okay, so 2x plus x squared. And then from there, I would like the 0.13 is on that curve. Okay, I'll believe them. Let's put in the 0.13. Here we go. Put the 0.13 in. And, oops, that's supposed to be a comma. There we go. And yeah, I might as well label it. There it is. There's the 0.13. And we would like to know the, we would like to know the slope of the secant line if x is 2 to this point, and x is 1.5 to this point, and x is 1.1 to this point, all the way to 0.999. So all the way from, so they want 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different slope values. That would be a lot of button punching with your calculator. Please don't do it. Please use Desmos the way I'm showing you here. So I would like to maybe, I'll go a comma h of a. And there we go. And yes, I want a slider. Oh, it's not h this time. It's f. Function. There we go. A f of a. And, okay, right now a is 1, so it put the point on there, but I can slide it to whatever I like. Right there. The first one it wanted was 2. And there we go. 2 is up here. So now I want the slope from this point to this point. So slope, again, is, remember how I entered this? It would be f of a, which is the y2 coordinate, minus, and this time I don't need variables, this time I have a fixed point, so it's 3, all over, and it's going to be this point here, which I guess I could label, which is 2 in this case, but right now it's a, so I might as well just put a, oops, that's not where the a goes, there we go, a minus and 1, and there we go. So the slope between these 2 points is 5. And then, so there, go back to the, I've just answered this question. Now to answer the next question, it's super easy. All I have to do is change this to 1.5. Watch what happens to the point on the graph when I do that. Oops, missed the 1. There we go. Now it's closer. And again, if you want to see the secant line while that happens, you just set a secant line as y equals m, and then x minus, in this case, the point that I'm referring to isn't an a and an h of a. It's actually 1, 3. So I can just go x minus 1 plus, and then that would be h of 1. Or I could have just said 3, I guess, too, if you like. Oh, and it's not h, it's f. That's the second time I've made that mistake. Sorry. There we go. And, oh, wait, that didn't work. Hold on. Oh, f of 1. Sorry. There we go. F of 1, which I could have just typed in as, notice it's, so there's the secant line that I just made over there. Notice, because I'm not changing this number, I could just say it's just plus 3. There we go. And then as I move this point, it should move the line with it. There you go. You can kind of see it's happening. There we go. So that's how I want you to do the homework. If you were looking at this homework going, oh my God, a question like that, he's going to want like a million calculations. It's going to take me all day. No, it won't. If there's anybody who has a graphing calculator at TI-83, what I'm doing here, it's a little more complicated, but you can set it up so the TI-83 does all these calculations for you too, or a TI-84. Okay, that's about it. This is already longer than I thought it would be, but that's the second part of lesson 1.1. Now we'll give you a day or two to work on the homework, and then we'll see you again for lesson 1.2.